last two episodes we introduced you to FortiH, which is a different take on the Fort language. If you haven't seen those yet, I advise you to take a look at them first. It will make it much easier to understand what I'm talking about. You'll find the links in the description. Last time we learned that a compiled FortiH program is heavily segmented, with each segment holding a different data type. One for the code itself, one for characters, one for integers, one for string constants, and finally a transient one for the symbol table. We also learned how FortiH sizes them. The integer segment is sized by counting the number of array and variable definitions while compiling. The same goes for the character segment, only here we are counting the strings definitions. The size of the string segment is determined after compilation, when all string constants have been condensed at the beginning of the source in memory. But what about the code segment, or the symbol table for that matter? Well, we've seen in previous episodes that every compiler needs a tokenizer, a module that chops up the source code in handy chunks, called tokens. FortiH is a tokenizer as well. It does the job of both the usual for tokenizer as well those performed by the parsing words. But it also does some counting. For argument's sake, let's assume that every token generates a single FortiH instruction. That's a nice rough estimate to start with. We can refine that estimate by keeping track of the exceptions. We also know which words are defining symbols, like colon, string, variable, and so forth. And those will end up in the symbol table. So, let's see how this counting works. We need one variable for the code size and one variable for the symbol size. When we encounter a definition like 5-array foo, we might assume that we have to reserve 3 symbols. But that's not true. We actually compile nothing. So we subtract those 3 instructions that are never compiled. It's a definition though, so reserve 1 symbol. Now let's consider begin. As we've seen in the previous episodes, begin compiles to nothing. So again we subtract 1 instruction. Finally, it's clear it doesn't define anything. ToDrop is expanded to drop, so we need 1 instruction more. But it still doesn't define anything. An expression like column bar comes in with 2 tokens, but only 1 instruction, a jump, is compiled. So we need 1 instruction less. But it does define something, a word called bar, so we need to reserve a symbol for it. And that, my friends, is how FortiH calculates the size of the symbol table and the code segment. But still, we're not quite done. There's a thingy we haven't addressed yet. There's one single module in FortiH that does all the compiling. The rest of the FortiH compiler tells this module what to compile. Let's say we want to compile a word like toSwap. It is expanded to rot, toR, rot, rfrom, and compiled. But certain constructs can be optimized. And that's why certain words are handled by the optimizer. For instance, if we feed it a word like toR, it is channeled to the optimizer. The optimizer determines that an expression like rfrom followed by toR is absolutely useless. It's like taking a cup from the cupboard and putting it back straight away. So the final rfrom is removed. That's called dead code elimination. It removes what boils down to completely superfluous code. Let's say we try to compile drop instead. This one is passed to the optimizer as well. The complete sequence, if compiled, would read rfrom drop. But there's a perfectly valid instruction for that called rdrop. So rfrom is replaced by rdrop. That trick is called strength reduction. An expensive operation is replaced with an equivalent, but a less expensive one. The final one may be the most impressive. It's called constant folding. Let's say we compile 2. Nothing special here. Then we compile 3. Still nothing out of the ordinary. Now we compile plus. And that one is passed to the optimizer. It takes the already compiled 3 and turns it into a special instruction called 3+. It's like 1+. only it doesn't add 1 to the top of the stack but 3. But here's the thing. A 3 plus instruction can be optimized as well when the last thing compiled was a numerical constant. So it is passed through the optimizer again. It takes the already compiled 2, adds 3 to it, and compiles 5. Now, that's neat, isn't it? It allows you to define a constant like k and use it to size buffers without having to manually calculate how much 4K memory actually is, because that is all done at compile time. Note, this is not Fort. You cannot switch between compilation and interpretation. It's one or the other. So, in some sense, FortiH Optimizer is an integral part of its syntax. Now we've gone to great length to size the code segment, only to find that the optimizer has probably shrunk the code. But that's not a big problem. The initial estimation may not have been exact, but at least we didn't have to allocate some arbitrary chunk of code and hope it all fits. A small program will still require a small amount of memory, and a large program will obviously require more. But we never have to increase that amount. And when compiling is done, we're still able to pick up the slack by only slightly adjusting the size of the code segment. Well, there you have it. That's how FortiH works. I think it does a pretty good job of emulating the capabilities of the classical Fort architecture without actually implementing one. It also interfaces easily with the C language, up to the point where you can write entire C functions in FortiH. Tell me in the comments whether you want to hear more about that or if you want me to discuss the inner workings of some other Fort programs. And a like or subscribe would be very nice as well. Thank you. Anyway, I'm Hans Beesmer, and this was another episode of Back and Forth.